So here they tell us that we have a potential energy of a roller coaster cart. What is the potential energy of a roller coaster cart if the cart has a kinetic energy of 1600 joules and a mechanical energy of 2400 joules? So based off what they give us here, we know kinetic energy, KE, is equal to 1600 joules. And mechanical energy is going to be 2400 joules. They ask us, what is the potential? So we're trying to find potential energy. So from here, it's a really simple equation. So we know that we have, we know that our mechanical energy is equal to we'll say kinetic energy. We'll keep it the same, kinetic energy plus potential energy. So from here, it's really simple. We know our mechanical, we know our kinetic. So what we're solving for is we want to find potential energy. So we want to solve for this. So let's just subtract kinetic energy from both sides. So this would mean our potential energy is going to be equal to mechanical energy, ME, minus our kinetic energy. So from here, we can just plug it in. So potential energy is going to be mechanical minus kinetic. So we should get a difference of 24 minus 16 is 8, and then we keep the zeros. So we get a difference of 800 joules. Another way of looking at this, 1600 plus 800 would give us 24, right? If we added the two together, we could plug it in to make it work. So it's pretty simple. If you know mechanical energy and kinetic energy, if you know any two of the three, you can find the third really easily. So let's look at what happens when we're not given kinetic and potential energy directly, but we're asked to find mechanical. This is going to be our example one. We're trying to look at the different cases for how we use this problem or this equation. And as we're doing this, I'm going to make sure I get the notes updated for us. Okay. So let's take a look at our next problem. So here we have another one where we're talking about a car that's traveling on a bridge at some speed with a height of 40 meters. So we want to figure out what's our total mechanical energy. So let's write down what they give us. We know that the mass of the car is 3,000 kilograms. We have a speed here of meters per second. So we'll use that as our velocity. And we have a height of 40 meters. So here we want to find the total mechanical energy. So if we're to break down our problem, this is the info that we should kind of be able to pull from here, right? So we want to find the mechanical energy. We know the mass, we know the velocity, we know the height. So we can look at our equation, right? Mechanical energy is equal to kinetic energy plus potential energy. So if we want to find mechanical energy, we're going to have to find kinetic and then find potential and add those two together. So for here, it's pretty simple. We're just going to plug into each equation. We know that kinetic energy is equal to 1/2 mv squared. We know the mass and we know the velocity. So our kinetic energy should be equal to 1/2 of our mass, 3,000, times our velocity, which is 5. So let's simplify a bit. 1/2 of 3,000. It's going to be 1,500 times 5 squared is 25. So from here, we can multiply it out. So we're going to get, don't like that, 1,500 times 25. So we should get 37,500. So that would be our kinetic energy. For our potential energy, we know that we have a mass of 3,000 kilograms. Sorry. Potential energy, it's going to be mgh. So we're just going to plug into there. So we take our mass, 3,000, times our acceleration of gravity. So g we know is 9.8. So we don't have it given to us, but we know it's always going to be the same. Times our height, which is 40 in this case. So we'll multiply this out, 3,000 times 9.8 times 40. So we're going to get something pretty large. So we're going to get something in the millions, and that's okay. So our potential energy, we're going to get 1176, followed by 3 zeros. So we're going to have 1 million joules here, and that's our kinetic energy there. So total mechanical energy is just the two added together. So we have KE plus PE. Just the one. And then we can just add, we already have the number in our calculator. So we should get a total mechanical energy of 1. So a little over 1 million. So when we're talking about this in our unit, would be so doing this equation's pretty simple. We're just going to add kinetic and potential energy to find mechanical, or if we're given either one, we can kind of subtract to find the missing piece. So notice all we're really doing is we're applying both equations at the same time and combining our answer for this one. So we're gonna get some practice today working with mechanical energy. We'll see a couple problems that are just asking for us to use only this equation here. But what we're really going to look at today is how to evaluate changes in this mechanical energy. So we know mechanical energy is kinetic and potential put together. So we're going to look at how it changes in different cases. Okay. So we talked about the conservation of momentum before. So this idea that momentum before and after reaction was the same. We have this same idea with conservation of energy. So if we have an object that is some height off the ground, it has its highest potential energy at the top, and it has its highest kinetic energy at the bottom. So as an object falls, kinetic energy is changed into potential energy. So kinetic energy goes up as potential energy goes down until it gets to the bottom, in which case it's at the floor. So when an object falls, potential energy is changed into kinetic energy. Some of this is lost to air resistance and friction, but we're going to ignore these when we deal with our problems. So one way to help us kind of understand what's going on, we can say that the kinetic energy and the potential energy added together at the start is going to be the same as at the end. Because if we look here, it's the maximum plus 0. Here, potential energy is 0. So the energy has just been transferred between position, how high it is, and movement, how fast it's moving. So this tells us that we know that the energy is going to be the same. It's just changing from one form to another. So this is kind of our link today. So mechanical energy before is going to be equal to the mechanical energy after, or final and starting. We could break this down. We know that mechanical energy is kinetic plus potential is going to also be equal to the kinetic after plus the potential after. So the different scenarios today, we're going to be using either of these equations to kind of figure out what's the kinetic energy at the start, what's the potential energy at the start, what's the kinetic energy at the end, what's the potential energy at the end. So this is going to be our equation that we're using. We're going to kind of try to set it up the same way we did before with the momentum conservation problems, where we kind of split our paper into before and after. That way we can kind of use the same technique to analyze what's going on. So for this problem here, we're looking at an object being thrown upwards, and we're trying to figure out how high the ball travels. So we're going to kind of set this up the same way we did before. We know that the mass of the ball is 1.4 kilograms, and the velocity is 2 meters per second. So let's look at it this way. We have some ball with a mass m. And this ball is going to be thrown up with a velocity, and we know it's 2 meters per second. So this is kind of our starting conditions. We could say that this is our initial velocity, and the mass isn't going to change. The ball is not going to get heavier or lighter. So this ball is going to continue to travel up, up, up until it reaches the top here. So my question to you, right, if I throw a ball up in the air, when it reaches the top, so if I throw something up and when it reaches the top, what can we say about the velocity here at the very top of this arc? So at the highest point, we know that like our object, right, we can say is traveling up, 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 right? We could say it's going like this. When it gets to the highest point up here, it's going to start falling back down. So at the tallest point here, we're going to say that the velocity is 0. This is the second because it gets to the top and then it's going to start falling back down. We know that this is going to go up by some height h. And that's kind of our before and after. So if we split it, right, we have some height that we don't know. We'll call this 2 because this is at the end. And we have some velocity that we do know. It's 2 equals 0. For both these, we have some mass m, and mass is going to be the same. So for here, we don't know what the height is, and that's what we're going to solve for. So we're going to set this up. We know that the kinetic energy here plus the potential energy is going to be equal to our kinetic energy 2 plus the potential energy here. So we can plug in these values, or we can notice a couple things. Here, this velocity is 0. So our kinetic energy is going to be 0 because it's not moving. And here, this is on the ground. We know that the difference between these two, we can say, if this is some distance height up, we could say that potential energy here would be 0. So our initial potential energy is 0. Our final kinetic energy is 0. So really what this turns into is kinetic energy 1 plus 0 gives us kinetic energy 2, which is 0 plus our potential energy 2. So that's going to go away. So we got rid of these because this is at the lowest point, and this is 0. So here we can say that height is going to be 0. So that would make potential energy 0. And here velocity is 0, so that would make kinetic energy 0. So from here, we just plug it in. We know that kinetic energy is 1/2 mv1 squared. And we know that potential energy is mgh. So let's fill in what we know. We have our mass, we have our velocity. We have our mass. We have acceleration of gravity, which we know is 9.8 times our height. So from here, we can just solve. So 1/2 times 0.4, we get 0.7 times 4 is equal to 1.4 times 9.8, but 13.72H. And then we can just kind of do the math from here. So at 2.8 equals 13.72 height. And then we can divide both sides. So we're going to get something small. We'll get height is 0.20 meters. So this is kind of looking at the situation and seeing when kinetic energy and potential energy, we know that kinetic and potential before is going to be equal to the kinetic and potential after. We knew that we could plug in 0 for these because this is at the lowest point here. This is at its highest point, which means the velocity would be 0. And then we were able to solve using this. So we're going to look at another one of these tonight. But rather than me going through everything and not giving you a chance to try some of these out, what we're going to do is we're going to have you try a couple problems right now, and then we'll finish the rest of them tomorrow. So what I want you guys to do right now is we're going to have you work on problem 2 and 3 today. So I want you guys to try out problem 2 and problem 3 today. And we'll have a chance to go over them at the end of the period.